Good afternoon, everyone. I trust everyone had a nice lunch. It's very nice to be in this beautiful city, and I would like to thank the organizers for putting together a very nice conference and letting me speak in this venue. And of course, I would like to thank co-authors and all the people who are working on observations, and I know pretty much everyone here is working on observations. Without further ado, I will proceed. And first, we're going to talk about what we heard at the last conference, ICR5 in 2017 in Rome. And there was a summary that was put together by the attendants over there, and I'll let you read the words which are highlighted here. But there's one adjective which is important, and so that will be, if you remember one thing, that will have to be it. But in this talk, we're going to look at what has happened since then on those actions that were recommended to be done about improving access, reprocessing, rescuing, recalibrating, making sure data are kept forever. And that's going to be basically our guiding principles for the next few slides. Before we continue, I will also have a first look back at the global observation record, and then we look at those actions that have happened since, and then we look ahead at opportunities. So the first chapter of the global observation record was well illustrated yesterday in a presentation showing the Millennium Reanalysis. And I've listed here a few of those proxy records. Those are not measurements of the climate, they are measurements of the impact of the climate. But of course, I thought it would be interesting to show you an interesting proxy. And if you can read Japanese, you will see important metadata over there, which is giving you the type of grape that is being looked at for the harvest date. And the horizontal axis is showing you years since 1300s. And the vertical is showing you the date of harvest for Pinot Noir in Burgundy. And you can see this date has been receding from October to September now. And whether you may question what is happening there, because the metadata is telling you it's a single type of grape, then you can probably infer something about this. But there are other types of proxies which are, of course, less palatable, but also interesting. So this is chapter 1. This is the pre-instrumental era. So what's interesting about this is that we have long records. So that's longevity. Another chapter coming after is the instrumental era. It starts basically with Industrial Revolution, when people are able to manufacture objects that they can repeat with a certain level of accuracy. So those are instruments. Before that, it's very difficult to manufacture repeated copies of the same thing. And so we have measurements basically from the mid-1700s. Bottom right, you have the Central England temperature time series, which is actually an aggregate of measurements from several stations, not one station. Top right is a key ship, which is the steamship Savannah. It was the first transatlantic steamship. And this one, the log has actually been preserved and worked on by National Museum of American History, right hand. And if you look at the log, if you zoom in, you will see that the foremost information they have is the position, the date, the time, and the weather. So those are early records, and they are very interesting to look at. Of course, we have other records over land, but basically the major expansion only comes at the beginning of the 20th century. For the upper air, the expansion comes middle of the century. It's the same story for the ocean subsurface. Before 1950s, we have much fewer number of profiles. All those measurements are mostly in situ. I say mostly because there have been observatories making measurements of what they see through various apparatus. And through that, we get measurements, for example, of atmospheric extinction or estimates of extinction, which can tell us about volcanic eruptions in particular. So this is chapter 2. Then we're moving into the satellite era. And there are two aspects before I get to the satellite era I would like to remind here, is that what's interesting about instruments is that they tell us about something that we believe is true, as the veracity, and also something which is authentic. Those are not data that have been made up, authenticity. So the satellite era starts mid of the century, after various trials to launch things into the air for various purposes. But now it's for peaceful applications, at least on this picture. And this is a picture by NRL, a mosaic of images. And then we can start seeing cloud formations. And very quickly, there is an understanding that this can be used for weather. And in the 60s, we start having regular images for that. Then in the 70s, we have vertical sounding from space, infrared, microwave, ultraviolet. So that gives us some information about temperature, about humidity, and about ozone. It does not measure that. It gives us information about it. It's different. And in the 1990s, we start having a lot more information about the ocean surfaces. We've heard about how important that is in various reanalyses, from scatterometers and altimeters. In the 2000s, we start having various types of hyperspectral measurements. Hyperspectral in the sense they give us detailed information along the spectrum. So that's very interesting to infer information about atmospheric composition in particular. And also, very importantly, we start having the first atomic clocks in space. And those atomic clocks are very nice because they are being broadcast. The signals are being broadcast with very nice precision. So 1 part in 10 to the 9 or something like that, which is not the accuracy we have to observe the climate. But with that, looking at the impact of the weather signal into that, we can get information. We can also get very precise orbit determination thanks to GNSS and other techniques. And that we can look at very small changes in the gravity field, and that gives us information about underground water, which is very interesting because that's what we live on. So last chapter is in the 2010s, and it continues with new types of technologies and so on. But now one example I would like to highlight is the observation of photosynthesis of the plants. So that's something very interesting. So all in all, this is about remote sensing, but not only, because those satellites have made it possible to equip in situ systems with transmission and positioning. So now we have autonomous systems. We've had them since the 70s, but that has made it possible to observe in situ the poles, the mountains, and so on, and also observe the oceans with buoys or profiling floats going up and down the water column and sending back their measurements. And also various types of drones, like this example here, a sail drone, but there are other ones. One has been shown this morning, for example, for the atmosphere. And also in parallel, while we have this, we keep having more data and more resolution. So an example of a long-running series is this one from HERS and AVHR. It's a result of reprocessing, and it goes back to 1978. And what's key about this is that this reprocessing could be done because there is traceability. There is traceability of the procedures, of the data, of documentation, the software, everything that made it possible to reprocess that series. And this is new. We cannot reprocess everything. So this enabled the recalibration in particular. Now you can see the agreement with some relative transfer calculations, which are missing actually representation of the volcanic eruptions, which is why you see departures at those 2 lines there. So altogether, if we're looking at the data that have been assimilated in Reanalysis, there is an animation there. And you're going to see the coverage starting in the 40s. And then mid-century, you're going to see more data from the upper air. And then as we move into the 60s, we're going to start seeing a lot more data, thankfully, also through aircraft and more radiosondes. And then the 70s, the satellite ozone retrievals, infrared microwave sounders, atmospheric motion vectors by looking at differences between images. And then in the 90s, sea surface height, altimeters, soil moisture, and finally radio occultation with snow cover. So this is a complete picture of what we are using in Era 5. And in Era 6, it will be more complete. We'll also have some data from the oceans that will be coming in via the ocean reanalysis. So what we're looking after here is really to having reanalyses that are as exhaustive as possible in their diversity of input to represent all the components. So there are some myths that I would like to talk about data rescue in particular, which is that data rescue is about going back in time. Actually, no, it's the opposite. When you do data rescue, you're bringing back measurements from the past into the present so you can use them. Another aspect is that data rescue is trivial. So if anybody has this conviction, then I am very happy to hand over 4 million images, which are just waiting to be digitized and turned into numbers. Please come to me. So we've had a number of projects since ICR5 on data rescue. They were already happening. What has happened is to structure that. So at the bottom, you've got this paper by Barbara Shimane in particular, which is decomposing the tasks into various elements. And also we've had some great efforts on working with WMO international partners, putting together a data rescue portal where the guidelines for data rescue are being updated regularly. And also you can register projects so people can know what is happening and if resources are needed. But the big question is, are we going to need to do data rescue forever? Are we going to be always doomed to lose and forget? I think yes, unless we change something. And that something is that we need the data to be exchanged at some point. If they are not exchanged, they are kept under lock, then yes, they will be forgotten, and yes, somebody will have to rescue them. So this will never end. So I'm asking if it wouldn't be possible that we think of a solution that there is a fallback into the public domain after a number of years. This is one of the possibilities. So what's important to avoid having to deal with this problem forever is exchangeability of the observations. So if we're looking at data exchanges, and if we look at the picture today, it's actually not as straightforward as one would wish, and I'm only considering here the climate aspects of things. There are other considerations that may go in there. But at the lowest level, you have the individual records. They may be coming from stations, they may be coming from satellite instruments, actually. Then those data will typically be archived by the operators in their local copies, or they will actually send a copy because they don't keep one. So that copy will be picked up by someone else who will save a copy, and then that will go into a level 3, what I would call level 3, which is an integrated climate archive, and there are various places where archives are being made using different procedures, covering different types of observations, different explanations, different responsibilities, and so on. And above that, you have other levels where the work is being done to work on thematic integrations of that. For example, ICOADs, or looking at the World Ocean Database, for example, for the subsurface ocean. And some of that is being taken by other entities, either taking from the top or taking from the middle or even taking from the bottom, going back to data rescue. Taking that and going directly into another space, which may be CrewTem or GISTEMP or ISST or other types of products which are very important for climate. So we've got this mishmash of relationships, and it's not a straightforward road. And once in a while, in the Reanalysis community, we come along, we take a copy of some of those things, and we put it in our freezers. And then once it's in our freezers, it may stay there for a couple of years. And once in a while, a chef will come along, cook something, and the clients will come and they will enjoy those delicacies. But you can see that the process is not exactly linear, and there is probably some room for improvement in this. And the room for improvement would come if there is a clear responsibility of whose role it is to keep ownership or stewardship of the observations by type or by whatever it is. Until the responsibility is defined, there will be various groups trying to do basically the same things and correcting data in one places but not everywhere. So an example of work that's been going on has been on the reprocessing. I've talked about data rescue. So an example of reprocessing is here by the Copernicus Marine Service, looking at subsurface archives. And they showed in 2018 that by merging those two major databases, they could actually get a lot more ocean profiles. And that's no surprise because data were collected by different paths. So that's the value of reprocessing. Another example is to improve the quality. That's an example here with drifting buoys. A project has been financed by Copernicus Institute. And you can see two trajectories on the left, one before and right after reprocessing. And on the right-hand side, you also see the value of merging buoys coming, data from the same buoy coming from different archives. Another example of reprocessing is improving the quality of data. This is for satellite data from Meteosat. You can see before reprocessing, the coastlines are not exactly matching what the satellite saw, and after reprocessing, you get a much better match. Another example of understanding the data and now moving to reuse is knowing exactly what's happened with the data. This is an example here where I'm looking at small variations in the satellite zenith angle as the geostationary second generation Meteosat is orbiting. It's supposedly at a fixed position, but actually it's slightly moving. And those slight variations are actually inducing a signal. And if you don't take care of that signal, you will get a map which is shown on the bottom right-hand side. The principal component of those variations will be like that. And that's not a climate signal. This is just a variation in the satellite. So that's an example of reuse, understanding the data. Another type of reuse is also looking at wrong station positions. This is for in situ, for example. So let's say we have a suspicion that we have the wrong position. Well, we have some methods in data assimilation. We can run the data with the original position and with the corrected position through the assimilation. And then we can look at the estimated observation errors according to the Rosier diagnostics, which are not perfect, but the difference between the two is something to be looked at. And then we can see if you go from the bottom 1.23 hectopascal to 0.5, then you must have a better position. So this is not proof, but it's a good indication that we're going in the right direction. Another example of reuse is considering, for example, the radiosonde observations. We're going to have a talk about this after. And it's going to show basically the value of that. But here I'm showing the example in the context of the changes that have been done to go from era 40 to era interim to era 5 to pre-era 6. So those curves are showing you the improvement. This is in a particular space, but it's on the order of 10–15%. When we use reprocessed radio sounds in gray, we can see that we're getting yet another improvement on top of that. So the improvement we're getting by reprocessing of the data or using them correctly are actually quite significant. So this is to put it into the greater context of why we bother about all of this. Then one more thing is that assessing observations can be done after a reanalysis. So after a reanalysis, we typically can look at the observation feedback. We actually had an effort of publishing it for era 20C. This proved to have very, very little user uptake, and in fact the dataset was retired. And so from era 5 we have not published the feedback, but we have made some statistics available, and I was happy to see that it's being taken on, and we look forward to seeing this feedback being compared with other comparable reanalyses, and going forward maybe we can come up with some way of comparing that more often. So this information you have after the production. It requires a lot of computing, obviously. The question is, cannot we use that before production? So yes, of course, this is an idea that's been around for a long time. And in fact, there are now tools which are very efficient to do that. In particular, there is the EUMETSAT RadSim radiant simulator, which has been used in some of the slides I've been showing, and will keep being showing later also. But we can do the same thing for the in situ. And then this is also helpful to help prepare the data. And so that I would call it, if we keep the music analogy, I will call it a prelude, because it's just what's going to happen before the concert. So it can inform us about departures, it can inform us about the quality of the data, and what we can do to improve the data or detect breaks or homogenize, and so on. I'm not saying homogenizing with respect to reanalysis, but understanding the breaks. So this is all useful to understand whether data are plausible. So this plausibility is also an important characteristic that we like to have in observations when we use them in reanalysis. So if we recap what we have done in C3S, with international partners have been to work on the rescue, the reprocessing of large data sets or of reference data sets, and the reuse. So if I focus on the large data sets, in the in situ community, we will typically refer to these as comprehensive networks. These are all data that have ever existed for a given type of measurements. And on the satellite world, those are more like fundamental data records of all the instruments of a given series, going back to the low level. And there have been some examples of data that have been generated as a result. I put here the websites, you'll have it later. And for reference data sets, those are the same idea, except those are probably from smaller missions or smaller records or smaller networks, but they all come with uncertainties. So the key difference is, by going through the reprocessing and not just using data from near real time, is that each datum is seeing an appendix to be given to it, telling the source of the data, the version of the data policy of the data, a quality flag for every single datum, and a suggested correction if need be. Those are all 5 characteristics that you wish to have when you're doing assimilation into reanalysis. And also for reference data sets, then we have uncertainty estimates. So you can look at some of those data that have been published from those websites. So what's next? Well, what's next is that we wish to continue acquiring more observations for reanalysis, but we know we're not going to be asking for more than what we need. And what we need is actually expressed in the GCOS requirements. The question is, how much do we need exactly? Because those are numbers. How do we translate that? So those are numbers that we can actually convert into what I would call a conformity index. This is inspired by the medical domain in the oncology for treatment of cancer. And we have a number of cells that we wish to observe, and that's by decomposing the whole spatial temporal domain into spatial resolution and temporal resolution. And then we have some cells that have been observed. If we take the ratio of that, this gives us simply a number between 0 and 100 that everyone can understand, and tells us how far we are from having observed every cell. So that's conformity. So if I'm looking at the conformity for era 5, for the in situ observations, this is not considering the satellite data, obviously, you can see where is the conformity, where is it good, and where it's not. And then it's very clear to argue why we need more data rescue in some regions, and Africa is clearly right in the middle of that. So in era 6, we've worked to put together, to assemble some data with partners. Those data are all published. This is explained in the poster. And this is the improvement we're getting. So that's the same metric, conformity, except here we're looking at difference. We can see it's a couple of percent, only a couple of percent, but that's going above the threshold. This is what you need to push that. So the new chapter that's being written is about the present times. So that new chapter of the global observation record is going to be very different, and it is already very different. We have up to the minute data, we have sub-kilometer scale, and this is no longer in the future. It's already happening now. We have actors which are no longer the traditional actors with large government agencies paying for everything. That's no longer the case. We have the private sector stepping in. We have citizens willing to help observe or buying weather stations and putting their data here. For example, this is Netatmo. The new sensors can auto-declare. They will automatically indicate their serial number so you know about the calibration. You can bring back those sensors to laboratories if you wish. And you also have details about other aspects of our system, including about living species. So an example here is also, for example, Spire, which is one company. This is not an endorsement in any means, but it's just indicating the possibilities that exist. And WMO is trying to organize that with a consultative platform. And the big player in there, so we have this train that's coming, which is a lot of data, and we are way lagging behind in terms of using this data. And the other train that's coming is actually those new methods to use directly the observations and directly get that projected without going through the assimilation the way we've been doing it so far. I'm not saying this is better, but there is clearly a need. So it's coming at the right time. It may help us exploit observations we've never used before, and also learn from the present times, which is very well observed, to map this back into the past where we didn't have the satellites. We can maybe do that through the in-situ. So I'll conclude with those 9 keywords. So I've spoken about them during the talk. They're actually interrelated. They have to do with the scope in one dimension, and the other dimension is the data management. So what we want is veracity. We come to observations because they are the truth. That's the first thing. We also come to them because they're authentic. We also want them to be somehow realistic, so that's the plausibility. So that's the first column. Now, the authenticity can only be established if you've got traceability. That traceability tells you who you got the data from. Are they legitimate? Is somebody working on it? And who is working on it? That's the responsibility. This person will ultimately have to take the responsibility for making the changes, for issuing a new version. This is the go-to person if you find data. If you've got campaign data for radio sounds, you know you should go to. You should go to IGRA. If you don't go to IGRA yet, you need to go to IGRA. That's an example, but this needs to be done for the whole observing system. There are other possibilities, of course, but the data must end up at IGRA. Then, above that, there is the fact that we want data that we can use. So we want long records, longevity. We want data from as many components as possible. That's exhaustivity. We cannot afford to start missing data today from the present observing systems. Otherwise, we're going to have to work on data rescue later. So this needs to be fixed very quickly. How? Through data exchanges. This exchangeability needs to be put in place right now. WMO has issued new recommendations. Actually, it's a resolution 1. But it needs to be adopted and put into force. We need to stop talking about it. It must be a reality. And then the last thing is we also want to make sure that we're getting data for what we need, and that's conformity. So I will stop here, and will thank you for your attention.